Welcome to Mrs. Strang's first podcast. Yay! In this lesson, we're going to learn about populations. This will cover Chapter 5 in our book. Feel free to come back and watch this video as many times as you want, and if you're listening to this during class, feel free to pause and ask questions when you need to. Let's begin our lesson by talking about sea otters. You know, when I was in 2nd grade, I did a book report on sea otters, and I titled it, Sea Otters, Friend or Foe? So, as I continue, be thinking, are these adorable little guys friends or foes? Sea otters are important members of the kelp forest community in America's Pacific Northwest coast. This forest is made up of algae called giant kelp, with stalks up to 30 meters long and smaller types of kelp. The kelp forest provides a habitat for a variety of animals. Sea otters need a lot of energy to stay warm in cold water, so they eat large quantities of their favorite food, sea urchins. Sea urchins, in turn, feed on kelp. The relationships among this food chain set the stage for a classic tale of population growth and decline. A century ago, otters were nearly eliminated by hunting. Sea urchin populations increased greatly, and the kelp forest nearly disappeared. Why? Because the kelp was being eaten to the bare rocks by hordes of sea urchins. The future of the kelp forest looked grim. And then, sea otters were declared an endangered species and were protected from hunting. With hunters out of the picture, otter populations recovered. Yay! Sea urchin numbers dropped dramatically. Kelp grew back, but now some otter populations are shrinking again because otters are being eaten by killer whales. To better understand why populations such as these change as they do, we turn to the study of population biology. Okay, Chapter 5, Section 1, How Populations Grow. There are 3 important characteristics of population. They are geographic distribution, density, and growth rate. Geographic distribution, or range, is the area in which a population lives. As you'll recall from our last chapter, populations are a group of species that live in a particular area. So this is wherever that particular population lives. You can see on our slide there that could be anywhere in the world, but there's a particular example of butterflies. You can see that that species of butterflies has several different variations, and they all have their own geographic distribution. Some species live in the northern part of South America. Some people live further south. That's just their geographic distribution. The second thing that affects populations are their population density. Density is the number of individuals per unit area, like the number of people in a square meter or kilometer would probably be more realistic. You can probably only fit like 4 people in a square meter, but you can fit a lot in a square kilometer. So a population density is the number of individuals per unit area, and you can kind of define the unit, how big you want that to be. A square mile, square kilometer, it's up to you. You can see on your slide how dense populations are all across the globe. You'll see Canada, and further up north and down south, there's not a lot of people. It's not very dense. The population is not very dense. It's pretty dense. You can see up near New York. It's very dense in Europe. It's very dense in India, and it's very dense in certain parts of China. And then you can see there's just a range pretty much everywhere else. But, the more cold places like, let's say Alaska, have very low population densities. The third thing that affects populations is growth rate. Growth rate is how quickly a population can increase or decrease in size. There's another picture on your slide of the growth rate of certain populations in percentages. You can see some grow really quickly, like certain places in Africa, Saudi Arabia, a couple other places in the Middle East, and then it goes fairly slowly in the United States, Asia, and pretty slow up. Well, actually, there's no data for Greenland or Antarctica, probably because, no one lives there. But anyway, not the point. Let's move on, shall we? There are 3 factors that can affect population size. Number 1 is the number of births. Yay, look at all these cute little babies. Aren't they adorable? Yay. The second is the number of deaths. And you can see on your picture that's the death rate of certain parts of the globe. And third is the number of individuals that enter or leave a population. If it's entering a population, it's immigrating into that population. If it's leaving the population, it's emigrating. So you can see that little duck swan creature is emigrating from one population and immigrating into another. So like I said, populations increase through births and immigration. And like this picture shows, immigration is the movement of individuals into an area. Populations can get smaller through deaths and immigration. And again, immigration is the movement of individuals out of an area. So you can see in this case, some of the individual insects are getting eaten and thus are out of that population. Or you can see some brown beetles will move to the green beetle area. So the brown beetle there on that cool red squiggly line is immigrating from its population and immigrating into the green insect population. The next thing we're going to talk about is exponential growth. Exponential growth occurs when members of a population reproduce at a constant rate. This growth pattern is shown in a J-shaped curve. As the population grows, the number of reproducing members keeps rising. Thus, the population goes faster and faster. You know, one person has one kid, or yes, we have to have two people. Okay, two people have one kid. That one kid has two more kids, and so on and so forth. And eventually you get so many kids, it makes this J-shaped curve. Eventually you have so many kids that are having so many of their own kids that it's growing exponentially. Under ideal conditions, with unlimited resources, a population will grow exponentially. In nature, however, exponential growth does not go on for long. Resources are used up in time, and this causes population growth to slow or stop. That doesn't mean that there are no more babies being born. It just means that the growth rate or the speed at which this population is growing slows down a little bit. Predators and disease also slow exponential growth. This is a graph of the human population. This is very, very, very interesting. You can see many years ago, the population rate was very slow. There weren't a lot of people. Many people died of disease and wild animals and all sorts of other people. I mean, life was just crazy a long time ago. You know, we didn't have the protection and technology that we have today. You'll see, though, as we get closer and closer to time 0, which is way far on the right, which is where we are now, it starts to speed up. There's a few bumps in between like 2000 and the 0, and one of those dips is actually the Black Plague, which is very interesting, I think, because that had such a significant impact in the growth of the whole human population. But anyway, as you get closer to time 0, which is now, you can see that it increased exponentially because now we have greater access to food and shelter and technology. We have vaccines, we have antibiotics, things that are helping people live a lot longer and be able to survive and reproduce, which is something that was unheard of a few thousand years ago. So, you may be asking yourself, what happens when this exponential growth hits a limit? Well, that limit is called a carrying capacity. As a resource becomes less available, like grass or some type of food, the growth of a population slows or stops. This is called logistic growth because it's logical that things can't grow on and on forever. Logistic growth is shown by an S-shaped curve. Remember, the other exponential growth looks like a J. Logistic looks like an S. Logistic growth occurs when a population's growth slows or stops following a period of exponential growth. So it'll grow exponentially for a while. You can see if you just kind of covered up that that bluish part of the line, you can see it goes up exponentially, but eventually it slows down. For example, if a food resource starts to run out or space becomes limited, because remember, space and light are also resources, a population that was growing exponentially may start to exhibit logistic growth. For example, in the human population, we are reaching our carrying capacity. You saw that we do exhibit exponential growth now, but eventually we are going to hit our limit, and we're getting pretty stinking close. The population size when growth stops is called carrying capacity. Now, that doesn't mean that babies stop being born. It just means that the growth rate stops. There's about the same number of births and deaths. It's not more births than deaths. Carrying capacity, again, is the number of individuals of a specific species that a specific environment can support. So in any area, there's a certain carrying capacity. There's a certain amount, a certain level of resources that an area can handle. And once it goes over that limit, it's that the birth and death rates will kind of equal out, and you'll get that nice S-shape curved. So that concludes section 1 of chapter 5. If you would please answer the questions in your note packet, and then you can feel free to move on. Chapter 5, section 2. All right. I'm going to talk now about the things that can limit that exponential growth, things that affect the carrying capacity of a place. A limiting factor is anything that slows the population's growth, and there are two types. There's density-dependent limiting factors that rely on population size. Like if the population gets too big, then they're more likely to spread diseases or have parasites, or there's more likely to be a lot of competition. And then there's density-independent, which are things that don't rely on population size, like natural disasters. It doesn't matter how many people live in a country. It doesn't affect whether or not a hurricane's going to hit. But let's go back to density-dependent limiting factors. They rely, like I said, on population size, and they can include things like competition, predation, parasitism, and disease. Competition occurs when organisms are using the same ecological resource at the same time, like when trees are competing for light in the rainforest. Predation occurs when one organism captures and feeds on another organism, like we talked about in the last chapter. The organism that gets eaten is the prey, and the organism that eats the prey is the predator. The predator-prey relationship can affect the size of both the predator and prey populations. For example, a decrease in the prey population will be followed sooner or later by a decrease in the predator population, because there won't be as many prey for the predators to eat. The other things that can affect the density-dependent limiting factors are parasitism and disease, like the Black Plague. Remember when I talked about how the human population had a huge decline in growth rate because of the Black Plague? Well, that was a disease because there's so many people living in one area. The population was so dense that it affected the ability for people to survive and reproduce. The second type of limiting factors, like I said, are the density-independent limiting factors that don't rely on population size. They include natural disasters like hurricanes, tornadoes, floods, landslides, all sorts of devastating things like that, and human activities such as damming rivers. Damming rivers doesn't seem like it should be that big of a deal, but it actually is, and it kills a lot of wildlife, and it changes just the shape and the landscape of many areas and kills a lot of organisms in the process. When one of these factors occurs, many species show a rapid drop in population size. Like when there's a hurricane or a flood, it's devastating to all the organisms, plants and animals in an area. That concludes Section 2, Limits to Growth. Again, all of these things can limit the carrying capacity of an area. Chapter 5, Section 3, Human Population Growth. Like I talked about earlier, the human race is growing at an exponential rate currently. The size of the human population tends to increase with time. For most of human existence, the population grew slowly. But about 500 years ago, the population began growing faster. Agriculture and later industry made foods more available. Improved sanitation, medicine, all of that reduced death rates. However, birth rates have stayed high in most places. So basically, there's been a lot of births throughout all of time, but before, death rates were very, very high because things weren't clean, we didn't have the medicines we have today, and so forth. All of this led to exponential growth. Today, the human population continues to grow exponentially. Demography is the study of human populations. Demographers try to predict how human populations will change over time. Birth rates, death rates, and the age structure of a population will help predict why some countries have a high growth rate while other countries grow more slowly. Again, birth rates are the rate at which babies are born, and the death rates are the rates in which individuals pass away. Over the past century, population growth in the United States, Japan, and much of Europe slowed greatly. Demographers called this shift a demographic transition. The transition began when death rates fell, causing a brief rise in population growth. Then birth rates fell, slowing population growth, and most people live in countries that still actually have a high population growth. Demographers use age-structured diagrams to help them predict population growth. An age structure diagram is a bar graph. See the little bars going on the left and right? It shows how many people of each gender and in each age group live in that population. And in this case, you can see the graph that's talking about the population of people in the United States and a few other countries. To predict how the world population will change, demographers need to think about the age structure of each country as well as the number of people with fatal diseases, including AIDS. This concludes Chapter 5, Section 3. Take a minute and answer the questions in your notes. Congratulations! You finished the Chapter 5 notes. Please feel free to go back, rewatch any parts that you didn't understand, or ask me any questions that you need to. But yay! You're done! You finished! Woo-hoo!